Today you are witnessing a colossal industrial sawmill built to process giant sequoia logs of an
This is a giant sequoia, nearly 1,000 years old. Its sheer size forces the factory to rely.
Every truck enters the exact lane and position. A deviation of just a few centimeters is enough to block the entire processing line behind it. Even the act of releasing the restraints follows strict safety protocol. The log is so heavy that any uncontrolled shift is unacceptable. We place the log onto a roller bed to begin washing and debarking before scanning the internal core.
The surface must be completely clean. Any remaining debris would distort the scan results and rapidly dull the cutting blades during the sawing process. Debarking exposes the structural wood beneath. Bark and wood residue are collected separately, never allowed to mix with load-bearing beams.
From this point forward, each giant sequoia log is managed as an engineered structural component, no longer treated as raw wood. These identification codes allow full traceability, from internal core scan results and cutting paths, through drying and treatment. The wood record is created the moment the log enters the facility. One incorrect parameter is enough to disrupt the entire production line.
Before any cutting begins, we must know what lie inside. Hidden cracks, internal voids, or structural weaknesses. Ultrasonic scanning reveals the internal structure. Any zone with a risk of cracking is excluded from the primary load-bearing beams.
X-ray inspection forms the second layer of verification, detecting dead knots and internal voids that ultrasonic scanning may miss.
Not every part of the log is suitable for load-bearing beams. We classify each section according to its structural grade. This is the moment the factory decides how to cut, maximizing beam length, thickness, and structural safety. Marking directly on the log ensures the saws follow the calculated map with absolute precision.
And this is the heart of the factory, the large block sawing zone.
The clamps must lock completely. Even the slightest vibration would ruin a cut weighing several tons. Large format bandsaws are used to break the sequoia trunk into primary beam slabs.
The blade must be cooled and cleaned continuously. The wood density is extreme, and the cutting width is far beyond standard scale.
Every cut creates a structural surface. From here, we begin shaping the future beams. Incremental feeding allows precise control of slab thickness, keeping dimensional deviation to an absolute minimum. These slabs will be cut further into thick beams designed for load-bearing bridge structures. Beam thickness between 200 and 400 millimeters forms the foundation for heavy load-bearing structures. Immediate sorting after sawing prevents any mixing of quality grades further down the line. End trimming removes crack-prone sections and brings each beam to its exact design length. Structural beams are not allowed to exceed curvature limits. Any bend will cause alignment errors during bridge assembly.
Proper stacking allows air to flow evenly, preventing moisture buildup and structural deformation.
Rough beams must be surface stabilized before entering deep drying. Now comes the most critical stage, drying structural timber. Timber used for bridges must reach a controlled moisture level, typically between 12 and 18%.
Convective airflow removes moisture in a controlled way, preventing thermal shock to the wood.
We don't measure a single point. We measure the entire batch, because every beam behaves differently. Dry too fast and the wood will crack. Dry too slow and it will miss specification. Everything must follow the correct curve. After drying, the wood is not used immediately. It must first be allowed to equalize. Equalization stabilizes beam dimensions before precision processing begins.